Today we are going to learn about mastering ROC curve interpretation for better models. We will explore how to interpret ROC curves effectively, allowing you to assess model performance and make informed decisions on model improvements.
Welcome to our session on mastering ROC curve interpretation for better models. In this introductory segment, we'll set the stage by explaining what ROC curves are and why they matter. ROC, or Receiver Operating Characteristic, curves are graphical plots that illustrate the diagnostic ability of a binary classifier system as its discrimination threshold is varied. They are essential for evaluating the performance of classification models, particularly in distinguishing between two classes. By the end of this video, you'll have a comprehensive understanding of how to use ROC curves to assess model performance and make informed improvements. Let's dive in.
The ROC curve is fundamentally a plot of the true positive rate, TPR, against the false positive rate, FPR, at various threshold settings. The TPR, also known as sensitivity, measures the proportion of actual positives correctly identified. Conversely, the FPR indicates the proportion of actual negatives incorrectly classified as positive. A key factor to consider is the threshold setting, which directly impacts both TPR and FPR. As the threshold varies, the balance between sensitivity and specificity changes, affecting the ROC curve shape. The diagonal line in the ROC plot represents a random guess scenario, where the classifier has no discrimination capacity. Understanding these components is crucial for interpreting what the curve tells you about your model's ability to distinguish between classes.
The true positive rate, TPR, and false positive rate, FPR, are critical metrics when evaluating classification models. TPR, or sensitivity, shows how effectively your model identifies actual positive cases, which is vital in contexts like medical diagnoses where missing a positive case can be costly. FPR, on the other hand, measures how often your model incorrectly classifies a negative case as positive, reflecting the type I error rate. Balancing these rates is essential. A high TPR with a low FPR is ideal, but often a trade-off must be made depending on the context of use. Effective ROC curve interpretation helps you make informed decisions about where to set thresholds, optimizing for either sensitivity or specificity as required by your particular application, managing risk more effectively.
The shape of the ROC curve provides insights into your model's performance. A curve that bows sharply towards the top left corner of the plot indicates a model that performs well, with a high true positive rate and a low false positive rate. The area under the curve, AUC, is a single scalar value that summarizes the curve, with values closer to 1 indicating better model performance. Ideally, the ROC curve should be convex. A concave curve suggests that the model's performance is less than random. By analyzing the curve shape and the AUC, you can assess whether your model is effectively distinguishing between classes, guiding further refinement and optimization.
Choosing the right threshold is a crucial aspect of model performance. The threshold determines the point at which the model classifies observations as positive or negative. Adjusting this threshold affects the true positive rate and false positive rate, creating a trade-off between sensitivity and specificity. For instance, lowering the threshold may increase the TPR but also the FPR, depending on your model's context, such as prioritizing sensitivity in healthcare applications or specificity in financial fraud detection. The threshold choice directly impacts the ROC curve, altering its shape and the AUC. Understanding how different thresholds affect model performance allows you to tailor your model's predictions to better meet specific application needs. Comparing ROC curves across different models is a powerful way to evaluate which model performs best. By examining the area under the curve, AUC, for each model, you can quantitatively assess performance. A higher AUC indicates better model discrimination ability. Visually, the model whose ROC curve is closest to the top left corner typically performs best. This comparative analysis helps in selecting the most suitable model for your needs, ensuring a balance between sensitivity and specificity. It's also a useful tool for identifying potential overfitting or underfitting. A model that performs well on training data but poorly on unseen data may show a distinct ROC curve pattern, guiding further model refinement. There are several pitfalls to be wary of when interpreting ROC curves. Firstly, AUC values can be misleading, especially if there's a class imbalance. A model might show a high AUC by predominantly predicting a majority class correctly. Additionally, relying solely on ROC curves without considering other metrics or domain-specific requirements can lead to suboptimal model choices. Misinterpreting the curve shape can also lead to incorrect conclusions about model performance. It's crucial to integrate ROC curve analysis with a thorough understanding of the application context, ensuring that model evaluation aligns with real-world needs and challenges. ROC curves are widely used across various industries. In healthcare, they help evaluate diagnostic tests, ensuring that models accurately identify diseases. In financial sectors, ROC curves assist in fraud detection, balancing the need to catch fraudulent transactions without overwhelming false alarms. Marketing campaigns can also benefit. ROC analysis helps in targeting the right audience by assessing model predictions for campaign success. In industrial settings, ROC curves are used in machine fault detection, optimizing maintenance schedules by predicting potential failures. These examples highlight how ROC curve interpretation must be context-specific to provide real-world value, adapting to distinct industry needs. Effective visualization of ROC curves enhances interpretability and decision-making. Start by clearly labeling axes and thresholds to ensure readers understand what the curve represents. Including the AUC value on the plot provides a quick performance assessment. For comparisons, color code curves of different models to maintain clarity. Using confidence intervals can offer insights into variability and reliability of model predictions. Interactive visualizations, where users can adjust thresholds and immediately see the impact on the ROC curve, can be particularly valuable, providing an intuitive understanding of model performance dynamics. These practices ensure your ROC curve visualizations are informative and actionable. In conclusion, mastering ROC curve interpretation is essential for evaluating and improving classification models. We've covered the fundamentals of ROC curves, delved into their components, and explored how to interpret and compare them effectively. By understanding the implications of TPR, FPR, and threshold selection, you can make informed decisions about model performance. We highlighted common pitfalls to avoid and emphasize the importance of context-specific analysis. Finally, adopting best practices for visualization enhances the clarity and utility of your ROC curve analyses. Equipped with these insights, you're now better prepared to leverage ROC curves for superior model evaluation and improvement.